Hi guys, welcome to this video. My name is John and I am a mathematics tutor specialising in tuition, support and guidance for A-level maths, A-level further maths, including 6-term examination papers and mathematics admissions test. Welcome to this video where we're going to take a look at radians. Okay, so one big question that I often get asked by my A-level students is, why do we have to make the change from degrees to radians at A-level? Why, when we do differentiation and integration involving trigonometric functions, do we have to use radians? Why can't we just stay using degrees? And this is it's a legitimate question, and it's not clear at A-level why this is, in my opinion. The short answer is that radians just make things easier. Okay, radians are a much more natural measure of angle size than degrees are, in a kind of theoretical sense, and they simplify a lot of the things that we need to do, including differentiation and integration. Now, unfortunately, the short answer doesn't really it doesn't really go into the details about why we might be justified in our choice of radians, our preference for radians when it comes to measuring angle size in mathematics. So what I hope to do in this video is to kind of give a bit of justification about why we might choose radians rather than degrees. The fact of the matter is, we could use degrees if we wanted to, but it would just make things just a bit more complicated than we would like them to be. Okay, and we'll see how. But another fact is that we don't necessarily have to choose degrees or radians. We've got an infinite number of possible ways that we could measure angle size. Okay, we're not limited to those two possibilities. We could choose, if we take a full turn, say, we can, if we choose degrees, then we split the full turn up into 360 equal units. Each one's what we call a degree, right? Or in the case of radians, it's a bit more difficult to imagine, but splitting the full turn up into 2 pi units, each one called a radian. So we can split a full turn up into as many units as we want to. It doesn't necessarily have to be a whole number. So it could be 1,000. It could be square root of 2. Units that we split the full turn up into. So initially we're going to assume that we've split our full turn up into k units. Okay, we're not assigning a specific value to k just for the time being. So it could be, in the case of degrees, k would be equal to 360. In the case of radians, k would be 2 pi. In the case of gradians, who uses gradians, right? K is going to be equal to 400. So k could be potentially anything. We're just not assigning a specific number to it, just for the time being. So let's say k units is equal to 1 full turn. Okay. Right. So for me, my story here starts with differentiation of the trigonometric function sine. Okay, so the trigonometric functions can be defined. I'm not going to do it in this video, but I might do it in another video. They can be defined for just a general angle measure. Okay, so irrespective of whether we're using degrees, radians, or whatever, we can still have trigonometric functions that are defined for any angle measure. Okay, so we're going to start with sine x, the function sine x, which is using this angle measure. Okay, and we're going to differentiate it. We're going to differentiate it from first principles, and we're going to see what happens. Okay, so sine x, if we differentiate it from first principles, we're looking for the limit as h approaches 0 of sine x plus h minus sine x over h. And it's just occurred to me that the way that I'm going to go about differentiating sine x from first principles here might be different to the way that you're used to on the current specification for A-level maths. I don't like, there's nothing necessarily wrong with it, but I just don't like the way that it's presented to you, differentiating sin x from first principles on the current A-level math specification. For me, it just seems fiddly. So I'm going to use an identity that's not on the A-level course now. Or it's not. I think it's still in the formula book. I could be wrong. I've not looked at the formula book for a while, so I can't remember exactly what's in there. But it's this identity anyway. Sin p minus sin q is equal to twice cos p plus q over 2 sin p minus q over 2. Okay, that's the identity that I'm going to use at this stage, because it makes things much nicer. And I prefer this identity. So this is equal to the limit as h approaches 0 of, what do we get? Twice, it's going to be cos, p is x plus h, q is x, so it's going to be x plus h plus x over 2, which if I simplify that a little bit, I get x plus h over 2. Sin x plus h minus x over 2, so that's just going to be h over 2 all over h. Which this 2 is in a bit of an awkward place for me for what I want to do, so I'm going to bring it down here. So this is equal to the limit as h approaches 0 of cos x plus h over 2 times the limit as h approaches 0 of sin h over 2 over h over 2. Now, this is a bit of a pain having the h over 2's all over the place here. If h approaches 0, then h over 2 approaches 0. So for all intents and purposes, I can replace all of these h over 2's just with h. And it really doesn't make any difference, okay? So just because it makes things a bit simpler, I'm going to replace the h over 2's with just h's. X plus h sin h over h. Okay, this bit's easy. So this limit is just cos x. But what about this limit? Now, I know what you're going to say. This limit's equal to 1. And yes, it is under certain circumstances. And that's what we're getting at in this video, potentially. This limit is not necessarily equal to 1. It's only equal to 1 under certain circumstances for certain values of k, it turns out. Okay? For degrees, for example, this limit is not equal to 1. If we use degrees, this limit is not equal to 1. Far from it. So, we need to investigate this limit. I think you might already be able to guess if the value of this depends on our choice of k, then when the limit of this is equal to 1, can you guess what value of k we might need to choose? If not, okay, keep watching. So we need to investigate this limit, okay, if it exists. So how we're going to do that? So we're going to look at the following diagram that I'm going to draw. So maybe make a note of this if it's useful for you, but we're going to concentrate on that limit right now. So to figure out the value of that limit, we're going to use the following diagram, okay? So we're going to have a sector of a circle of radius equal to 1, okay? Not very well drawn, but never mind. So that's O, that's A, that's B. And what I'm going to do is I'm going to form 2 triangles here, 2 right angled triangles. So one is going to be here, call that point C. And just extending this line out a bit and then drawing a line vertically upwards here, get the point D. So we get these 2 triangles. One is smaller than the sector, or has an area which is smaller than the sector, another which has an area which is evidently greater than the sector. And it's that we're going to be using. Okay, we're going to be comparing the areas of these different regions. So the area of triangle OAC is going to be equal to a half OC times AC. Okay, remember that OA is equal to OB, which is equal to 1. So that means that OC is going to be equal to cos H, because cos H would be equal to OC over OA. OA is just equal to 1, so OC is just equal to cos H. Similarly, AC is going to be equal to sine H. So that's the area of OAC. How about the sector OAB? Okay, so I'm not going to use the formula half r squared theta for this because that uses the notion of radians, right? In that formula, half r squared theta. Remember at GCSE you had a different formula for finding the area of a sector, that but you used degrees to find the area of a sector then, and it was a more complicated formula. Okay, well, we're going to derive a corresponding formula for the general case here. So if we think about a full circle, which has area pi, if it's got a radius of 1, then it's got an area of pi. And we're going to think about a sector of that circle. Okay, so what proportion of the full circle is this sector? Well, it's h over k. So its area is going to be h over k times pi. Okay, the area of this sector. So clearly, we've got that half cos h times sine h, which is the area of this triangle OAC, is less than the area of the sector, which is h over k times pi. Now I'm going to rearrange this a little bit. So let's have a look. What do I get? I get sine h over h, and these are all positive quantities, by the way, so I can multiply and divide through without worrying about signs, inequality signs flipping and things like that. So I'm just dividing through by h and then multiplying through by 2 and dividing by cos h. Okay, so I get this inequality. Right, now I need to consider the larger triangle. I know the diagram's a bit wonky, isn't it? But never mind. So the area of triangle ODB is equal to, it's going to be a half OB, which is 1, times DB, okay, DB, which is a half times 1. So DB, let me have a think. So tan H is going to be equal to DB over OB. OB is equal to 1, so tan H is equal to DB. So tan H, and I'm going to write it as, because I've got causes and sines and things over here, I'm going to write it as sine H over cos H. So this is 1 over 2 sine H over cos H. And therefore, this is going to be greater than, so this area here is going to be greater than this area of the sector, h over k times pi. So again, I'm going to kind of rearrange things a little bit here. So what do I get? Sine h over h is going to be greater than 2 pi over k times by cos h. So I can combine these two inequalities now. Okay, sine h over h was less than 2 pi over k times 1 over cos h. That's what came from considering comparing the area of the smaller triangle with the sector. Now comparing the area with of the sector with the area of the larger triangle, I get that sine h over h is greater than 2 pi over k times cos h. So I can add that in here, 2 pi over k cos h. Okay, so just to give myself a bit more space, I'm going to clear this off. And what we're going to do now is we're going to look at the limit. We're going to take limits of each of these as h approaches 0. Okay, so if this is smaller than this, is smaller than this, then the limit of 2 pi over k times 1 over cos h is less than or equal to the limit as h approaches 0, as h approaches 0 of sine h over h, which again is less than or equal to the limit as h approaches 0 of 2 pi over k. Sorry, that should have been cos h, not 1 over cos h, times cos h of 2 pi over k times 1 over cos h. Okay, so this limit, because cos h approaches 1 as h approaches 0, this limit is 2 pi over k. So 2 pi over k is less than or equal to the limit as h approaches 0 of sine h over h, which is less than or equal to the limit of this as h approaches 0. Again, cos h approaches 1, so that's going to be 2 pi over k. Conclusion. Well, the limit of sine h over h is kind of sandwiched between these two values, which are actually the same value. Okay, and this is a theorem in real analysis. If you do go on to university to do mathematics, you'll do some real analysis. You'll prove what's called the sandwich theorem, sometimes a sandwich rule or squeeze theorem or something like that, where you've got three sequences, one's sandwiched between the other two, and if the two on the outside have the same limit, then the one in the middle has the same limit as well. Seems obvious, but it, as with anything in mathematics, it requires proof. So here we can say that the limit as h approaches 0 of sine h over h is equal to not 1, but 2 pi over k. So what's the point of all of this? Well, what we've shown is that the derivative, when we differentiated from first principles, the limit of, what was it, as h approaches 0 of sine x plus h minus sine x over h, we'd got to the point where we'd shown that this was equal to cos x times this limit. So now we can say it's going to be cos x times 2 pi over k. So 2 pi over k cos x. Okay, so what we can see then is that our derivative of sine x is going to be different. It's got something to do with cos x, but it's not just going to be cos x necessarily. It's going to depend on how many units we choose in our full term. Okay, if we choose 360 degrees in a full term, 360 units, our derivative is going to be pi over 180 cos x. When we differentiate sine x using degrees, we get that the derivative of sine x is pi over 180 cos x. Okay, if we choose k to be 1,000 units, we're going to get our derivative of sine x to be pi over 500 cos x. Okay, so it really depends on what we choose for our value of k. But what would be nice here? Well, if the derivative of sine x was equal to cos x, right? Okay, so if we chose k to be equal to 2 pi, then we'd get that the derivative of sine x is equal to cos x. So if k is equal to 2 pi, then the derivative d by dx of sine x is equal to just cos x, because we get 2 pi over 2 pi times cos x, which is just 1 times cos x. Okay, so this might be one of the ways that we can justify our choice of radians when it comes to measuring angles. I'm not saying that this is the way that we necessarily justify it, but this is just one of the possible ways. Okay, there might be other reasons why. I don't know what the historical reasons are necessarily for choosing radians, but this could be used as at least a justification. Okay, so hopefully that brings some clarification to the situation, but also I hope it has raised a few questions for you. And if you do have any questions about anything that I've said in this video, then please leave a comment in the comment section and I will be happy to answer your questions. If you did find this video useful, please hit the subscribe button and hit the like button, and share this video with anybody that you think might benefit from it. Okay, I'd be really grateful for any input from you. What kind of things could I be doing differently with these videos? What kind of things do you want to see? Because I can always remake this video and I can always make other videos, and I'm happy to do so. Please be aware that I don't make any money from making these videos. I do them because I want to help people. Okay, I make them for free because I want to help you. So it would be really great if you could show your support so I can continue making these videos and I can continue helping you. And with your feedback, hopefully make these videos better in the future. So with that, I'm going to say thank you for watching, and I will see you in the next video.